Hello everyone, and welcome to this explainer for Lecture 5 of Basic Electromagnetism. The theme for today is polarization, which we write as P, and magnetization, M. We're going to dive deep into how real-world materials actually interact with electric and magnetic fields.
Okay, so we've got Maxwell's equations, and they work perfectly in a vacuum. But what about inside stuff, inside actual materials? That's the big question for today. We're going to look at the physical picture behind polarization and magnetization, their definitions, and the forces they create, especially torque.
And the answer is actually really elegant. We don't have to throw out our beautiful equations. Instead, we just add a couple of new terms to account for what's happening inside the material. Take a look at the highlighted relations here. We introduce this new quantity, polarization, that's capital P, into the equation for D, and we add magnetization, capital M, into the equation for B. They're basically correction terms. And right away, just from looking at these equations, we can figure out their units. Polarization P has to have the same units as D, which is ampere-seconds per square meter. And magnetization M must have the same units as H, that's amperes per meter.
All right, let's start with the electric story. Let's talk about polarization P. So what actually happens when you take a dielectric material, something like plastic or glass, and you stick it in an electric field?
Okay, so let's zoom way in, down to the atomic level. An external electric field comes along, and it starts pulling on the positive nucleus and the negative electron cloud, but in opposite directions. This causes a tiny little stretch, just like you see in the diagram, and that creates what we call a tiny electric dipole. Now, think about a whole block of this stuff. Inside the material, the positive end of one dipole is right next to the negative end of its neighbor, so they just cancel each other out. But what about the edges? At the surfaces, there's no neighbor to cancel them out. So you're left with this net layer of charge, and that's what we call the polarization charge. So how do we quantify this? Well, each of those little stretched atoms has something called an electric dipole moment, and we write that with a lowercase p. It's a vector, and it tells us the strength and direction of that tiny charge separation. Now, when we want to talk about the effect in the whole material, the macroscopic effect, we use a capital P for polarization. You can just think of it as a density. It's the average strength of all those tiny little dipole moments packed into a certain volume.
Okay, now let's switch gears to the magnetic side of things. And as we go through this, you're going to see a really beautiful symmetry here, what we call a duality, between the electric and magnetic stories.
So for magnetism, the story is pretty similar. But instead of separated charges, the fundamental source is a tiny circulating current. Remember, there are no magnetic monopoles, so the origin of magnetism is always a current vortex. A good way to picture this is an electron orbiting a nucleus. When you apply an external magnetic field, these little current loops tend to line up. And, you guessed it, just like with the electric dipoles, the currents on the inside of the material cancel each other out. But that leaves a single net current flowing around the surface, and we call this the magnetization current. And just like before, each of these microscopic current loops has its own magnetic moment, written with a lowercase m. So it follows that the macroscopic magnetization, that's the uppercase m, is defined as the density of all these magnetic moments in a given volume. The parallel is just perfect. But there's a key difference. Unlike an electric dipole, you can't ever separate the north and south poles of a magnetic moment. It inherently creates what we call a pure vortex field.
So we've got these microscopic things, lowercase p and m, and these macroscopic densities, uppercase P and M. So how do we formally connect the two scales? Well, the link between the tiny micro moments and the big macro effect is actually pretty straightforward. You just add them all up. In physics, the fancy way to add them all up is with a volume integral. It's the exact same idea as integrating charge density over a volume to get the total charge. So when you integrate the polarization density, capital P, that's the micro property, over a volume, you get the total electric dipole moment, lowercase p, for the whole object, the macro property. And the exact same logic holds for magnetism.
Okay, here's a really powerful way to lock these concepts in your brain. I call it Trinity memorization. The idea is to connect three things so they reinforce each other. First, the physical picture. Are we talking about displaced charges or little current loops? Second, the mathematical formula. The definitions like P equals Q times L, and the volume integrals that connect micro to macro. And third, the unit consistency. The units have to tell the same story. Let's check it. The unit for polarization P is ampere-seconds per meter squared. When you integrate that over a volume, which has units of meters cubed, you get ampere-second meters, and that is exactly the unit for the dipole moment P. When the physical picture, the math, and the units all line up perfectly, you know you've really understood it. This works for magnetism too.
All right, so we've defined what polarization and magnetization are, but what do they actually do? How do they interact with the world around them? Next, we're going to look at the fields they create and the forces they experience. This slide shows a really fundamental difference in the shape of the fields these things create. On one hand, you have a monopole, like a single-point charge. It creates a simple source field that just radiates straight out. It's a conservative field, which means if you take a path around a closed loop, the total work is zero. On the other hand, a moment, like a dipole, creates a field that is fundamentally a vortex field. It has a loop-like character. Now, technically, the field from an electric dipole is still a conservative field overall, but from far away it looks like a vortex. Why? Because the close-range contributions from the positive and negative charges cancel each other out.
So what happens if you take one of these moments and you place it in an external field? Well, it's going to experience a torque. That's a rotational force, and it tries to twist the moment to align it perfectly with the field lines. This torque, which we write as T, is the exact principle that makes a compass needle point north or an electric motor spin. But that's not all. Besides this rotational force, if the field isn't uniform, meaning if it's stronger in one place than another, the moment can also feel a translational force, a push that actually makes it move from one spot to another.
And here it is again, that beautiful duality. The equations for electric and magnetic torque look exactly the same. It's a cross product between the moment vector and the field vector. And what this cross product does is it calculates that rotational force that's trying to get them to line up. It's really interesting to notice the similarity here to the Lorentz force equation, which also has that J cross B term. Now, the unit for torque is the Newton meter. And while that has the same dimensions as energy, which is joules, they are physically different things. Torque is a vector, and we use the good old right-hand rule to figure out its direction.
Okay, let's wrap this up and see how all these new ideas fit into the big picture of electromagnetism.
So let's bring it all home. What's really powerful here is that we don't need to throw out our old physics. Take a core rule like the Poisson equation, which normally relates electric potential to electric charges. As this concept change shows, we can cleverly substitute the charge term with a new term derived from our polarization P. This means all our powerful, existing mathematical tools can now handle the effects of matter. It's not about creating new laws, but elegantly extending the ones we already have.
So we've seen how these microscopic moments create macroscopic properties that change the fields inside materials. The next logical step, of course, is to figure out how to harness this. In our next session, we're going to dive into conductors and capacitance. We'll see how these principles lead to real-world electrical components that are macroscopic versions of these moments, things like capacitors and coils. And we'll finally connect all of this deep theory back to the physics you might have learned in high school. Thanks for watching.